Okay, let's talk about magnetic field today. Magnetic field. So basically, magnetic field is a vector quantity. The symbol of magnetic field is B. Unit for it is Tesla. We use the capital letter of T to represent Tesla. And basically, magnetic field exists surrounding a magnet. For example, this is a magnet bar, where this end is a north pole, the other end is a south pole. So magnetic field is always directed from north to south. And since magnetic field is a vector quantity, so you must know what is the direction of the magnetic field surrounding a magnet. Magnetic field also exists surrounding a wire which carry the current of I. Okay, so you can use the right-hand thumb rule to determine the direction of the magnetic field. So if let's say this is a straight wire which carrying the current of I, so if you use the right-hand thumb rule, you'll find that the magnetic field surrounding the wire is in the anti-clockwise direction. And now, if you bend the wire into a loop, for example, this is a loop, and carries the current of I in this direction, for example. And again, you can use a right-hand thumb rule to represent the direction of the magnetic field. So in this case here, magnetic field will be directed in this direction, right? And if you further bends the wire into more loops or more turns, you can form a solenoid. So this one is called as solenoid. Okay, for example, the solenoid carries the current of I. So you can also use a right-hand thumb rule to determine the direction of magnetic field of B, right? So this one we call it as solenoid. This is a loop which carrying the current of I, and this one is a straight wire. Okay, so no matter it is a bar magnet or a straight wire or a loop which carrying the current of I, so of course the wire must carry the current of I, or a solenoid carrying the current of I, all this can produce the magnetic field. Right? So how can we calculate the magnitude of magnetic field? We can use a law, call it as Ampere's law, to derive out the expression of the magnetic field. So Ampere's law states that the total current enclosed by the Amperian path is equal to the line integral of magnetic field intensity, right? So where B is equal to mu H. So in this case here, H is called as magnetic field intensity. B, of course, is a magnetic field. So both B and H are vector quantity. It has its the direction, right? So if you use Ampere's law, you can derive it out for a straight wire. The magnetic field B is equal to mu naught I divided by 2 pi r, where I is the current on the wire, and r is the distance from the wire to the point of interest. So for example, if I refer to this straight wire, right? So from the wire to the point of interest, this is R. So you're able to find out what is the magnetic field at this point. Okay, for example, point X. Okay, so we can use this formula to find out what is the magnetic field at that particular point where it has a distance of R from the wire. So the direction of the magnetic field, you can use a right-hand thumb rule to determine what is the direction of magnetic field. Okay, because magnetic field is a vector quantity. And we can also use, derive out the magnetic field for a solenoid. So basically, magnetic field for a solenoid is equal to mu naught n I, where this small letter of n is the number of turns per unit length. So let's refer to a solenoid. So this is a solenoid. Number of turns here means how many turns of this solenoid, n turns, and the length of the solenoid is here. Okay, so where small letter of n is equal to the number of turns per unit length. So this expression is actually referred to the magnetic field inside the solenoid, okay, which is almost constant, right? So this point are the magnetic field, introduction of magnetic field, and how can we find out the magnitude of the magnetic field and also the direction of the magnetic field by using right-hand thumb rule. Okay, now let's further discuss. Okay, so if I have a wire which carrying the current of I, and I place the wire in an external magnetic field, right, of B. So what happened to the wire? The wire will experience a force, call it as magnetic force. So magnetic force is just like a normal force, which is a vector quantity as well. So you can write that FB or FM to represent the magnetic force. So force, as you know, that is a vector quantity. So what is the magnitude of the magnetic force? FB is equal to BIL sine theta, right? So where I is the current flow in the wire, L will be the length of the wire, and theta here is the angle between I and B, right? Angle between I and B. So this B here must be a B, external B with respect to the current carrying wire, right? So this B is not the B produced by the current itself. So you have to bear in mind that the magnetic force will be only exerted on the wire when you place a wire which carrying the current of I in an external magnetic field of B. Okay, so how can we find out what is the direction of the magnetic force here? Direction of the magnetic force can be determined from the rule, call it as left hand Fleming rules. Left hand Fleming rules. Okay, so where thumb representing the direction of the force, first finger representing the direction of the magnetic field, and the second finger representing the direction of the current. So just remember FBI, okay, to get what is the direction of the force. Okay, you must use Fleming left hand rules. Okay, must use left hand. Okay. Other than that, we can also determine, we can also find out what is the magnitude of the magnetic force. Magnetic force on a moving charge, right? That means when a charge is moving with certain velocity, so must be moving. Magnetic force exerted on the moving charge is QVB sine theta, where Q is the magnitude of charge of the moving charge, V is the speed of the charge, B is the magnetic field, and angle theta here again is the angle between B and V, right? So V is the speed of the moving charge. So there's one very special character of this of this moving charge when it is moving in an external magnetic field. So what happens if the moving charge, direction of the speed of the moving charge is perpendicular to the magnetic field? So what happens to the moving charge is the moving charge will move in a circle. So the charge move in a circle, and therefore the magnetic force is also equal to the centripetal force. So centripetal force is the force in a circular motion, right? Therefore, I can further discuss QVB is equal to mv squared over r. So what is the sine theta? Because we already stated that the Q and the V and B is perpendicular to one another. Perpendicular to one another means sine 90 degree means sine 90 is equal to 1. So the term of sine 90 is already can be ignored. Okay. So from here we are able to find out what is the radius of the circle made by this moving charge, right? So where the radius of r is equal to mv divided by qb. And now if you accelerate this moving charge with the potential difference of v, right? For example, the charge has a magnitude of q, and therefore the kinetic energy of the moving charge is half mv squared. So from here we know that v is equal to 2qv, where this capital letter of v is the potential difference to accelerate the charge, right? Potential difference to accelerate the charge, right? So from here, the speed of the charge, small letter of v here is the speed of the charge is equal to 2qv divided by m, then square root of it. So if we substitute this expression of v into this equation, and you will get a new equation to relate the relation of the ratio mass per unit charge. You will get a relation of mass per unit charge, which is equal to r squared divided by 2v multiplied with b squared, right? So why we need to use this information? Because this is the relation that we need to know so that we can apply in a device, call it as spectrometer. Okay, mass spectrometer. More specific should be mass spectrometer. Okay, mass spectrometer basically is a device used to separate the isotope of charge. So then we can find out different isotope with a different mass and charge. We can get a ratio, and from there we'll know that what is the size of the circle made by the moving charge, right? So other than this application, one of the application of what we learned here is we apply in a mass spectrometer. We can also apply in a device, call it as velocity selector, right? As given by the name here, velocity selector means you select certain velocity of the moving charge, right, in the this equipment. So where the velocity selector, for example, the velocity is v, so it's equal to E over B. So in the velocity selector, you have you apply the magnetic field and also electric field in the velocity selector. Then you vary the magnitude of electric field and magnetic field so that you can select certain velocity that you would like the charge have, right, by varying the magnitude of V and B. So this is the application of the magnetic force, and if the speed of the moving charge is perpendicular to the magnetic field. All right. So now, if we apply this magnetic force in motor, so magnetic force can be also, the concept of magnetic force can be also applied in motor, right? So in motor, okay, let's look at it. Motor. So for example, if I have a magnetic field, I create the magnetic field. not create the magnetic field, but I supply the magnetic field from the magnet bar here, and consists of the magnetic field of from pointed from north to south, and I have a loop, right? I have a loop which carrying a current of I in this direction, for example. So what happened to this loop is, right? So the loop will be rotating either in clockwise direction or anti-clockwise direction, right? Either in clockwise, anti-clockwise or clockwise direction with the speed, angular speed of omega. Okay, how could we determine what is the rotational motion of this loop? We are applying the concept of magnetic force. We are applying the concept of magnetic force to the current loop, which carrying the current of I. Okay, which carrying the current of I here. Okay, now if you put your eye on top of this loop, right, from the top view, so what can you see here is the loop, the conductor is now this, and the magnetic field is still directed from north to south, which is pointed to the right. So this is the magnetic field of B, and on this conductor, the current at this end, on the left end of the conductor, is pointed outwards, and the other end of the conductor is pointed into the pitch, right? Into the pitch. So then you use a left hand Fleming rules to determine the direction of force exerted on the left end of the conductor and the right end of the conductor. You'll find that on this end, right end of the conductor, the force is upwards, and on the right end of the conductor, the force is pointed downward of F, right? And therefore, this conductor will be rotate in a clockwise direction. Okay, will be rotate in a clockwise direction. So this one should be in a clockwise direction. Omega. Okay, so we know a term, call it as torque. Torque means a rotational force. So torque exerted on the wire here is equal to the cross product of lever arm and F. Okay, so where torque is equal to RF sine theta. So what is this theta? Theta is the angle between the F and R. So this is a F, and R is a term called it as lever arm, which is the distance from the axis of rotation to the line of action. So this is the line of action, right? So axis of rotation at the center of the conductor. And now RF sine theta. So since both of the forces here will create a rotational force in the same direction, and therefore the total torque or the net torque exerted on the wire here is RF sine theta multiplied with 2, right? And you will get R, right? R is what? Okay, if I assume that the there's a loop here, the width of the loop is W and the length of the loop is L, right? So which means this one is W, and therefore R is actually equal to W over 2, right? So R is equal to W divided by 2. Okay, so the net torque exerted on the conductor will be W over 2, F sine theta multiplied with 2. So F will be the force exerted on a current carrying wire in an external magnetic field. Therefore, the F will be BIL, right? And there's no sine theta here because the angle between B and I is perpendicular to one another. Therefore, sine 90 is equal to 0. Sine 90 is equal to 1. Okay, sine 90 is equal to 1. So now here we have additional one more term is sine 90. So I just write in here as sine 90. Then eventually, net torque exerted on the wire is equal to, here is multiplied with 2, yeah? So multiply with 2. The net torque exerted on the wire is equal to BIL omega sine theta, right? So happen L multiplied with omega. L multiplied with omega is actually referred to the area of the loop, which is here. Area of the loop. Okay, so I can change the term to become area. I will have BIA sine theta. So if the loop that we have it here consists of n turns of loop, therefore the net torque is equal to n BIA sine theta, or another term, another expression which is easier to remember would be Vena sine theta. Okay, so where the theta here is the angle between B and normal of A, where A is the area of the loop. So we have one new term. Is the product of I and A, right? So we call this as magnetic dipole moment. And we use a symbol of capital letter of M to represent the magnetic dipole moment. It's basically the product of N multiplied with I multiplied with A, or just INA. Right? So INA is called it as magnetic dipole moment, a term given to this, the product of these three terms. Okay, so that's how we apply the magnetic field concept to explain the concept principle of motor, working principle of motor. Right, so now, if we refer back to the definition, not definition, but the magnetic field, the term of magnetic field, we can actually relate this magnetic field to another term. We call it as magnetic flux. Okay, magnetic flux with the symbol of this phi. So magnetic flux is defined as the dot product of magnetic field and the area, right? And you will get BA cos theta. So when theta is the angle between B and normal of A. And the unit for the flux, magnetic flux, is Weber or Tesla meter square, right? So this is a definition of magnetic flux. So we can, why we need to know the terms of the magnetic flux, we are going to look at a law, right? Call it as Faraday law. So Faraday law. So according to Faraday law, the magnitude of the EMF induced is equal to the rate of change of magnetic flux. And if the loop that you have it here is n turns, then you just simply multiply with n. And there's another law, call it as Lenz's law. Lenz's law will tell you that the direction of the EMF induced in the coil or in the wire, right? So the direction of the magnetic flux, direction of the EMF induced is always opposed the change of magnetic flux. So this phenomenon, we know it as electromagnetic induction. Electromagnetic induction, right? So basically, how can you produce the magnetic EMF induced in the coil? So there must be a change of magnetic flux, right? So now there are a few ways for you to produce the changing of flux. So basically, you can change the flux by using, if let's say I refer back to the definition of magnetic flux. So flux is equal to BA cos theta. So you can change the B, you can change the A, or you can change the angle of theta. And if I have a moving conductor, right? So which is moving. Okay, let's say I have a conductor. This is a conductor moving with the speed of V in a region of the magnetic field of B. Then the EMF will be also induced in this conductor. So this type of EMF induced in the conductor, we call it as motional EMF. So motional EMF, where the magnitude of motional EMF in this case here is equal to BLV, right? So where L is the length of the moving conductor, which places it in the external magnetic field of B. Right, so this EMF motional is actually referred to the EMF induced, and we can apply this motional EMF in a device called it as generator, right? In the concept of generator. So you can prove it out that where the EMF induced in a generator is NBA omega sine omega t, which is a AC, right? Which is in the AC form, because it can be written in this form. E induced in a generator is E equal to E naught sine omega t. So it's in a sine wave form, right? So this is the EMF induced. EMF induced in a rotating coil, right? Which is moving with the angular speed of omega. Okay, this is a generator. And now we can apply whatever that you learned now, right? So the concept combination of the electromagnetic induction, right? And also the AC combined to apply it in a device called it as transformer, right? So basically transformer, there are two types of transformer. One we call it as step up transformer. One we call it as step down transformer. So step up transformer means the number of turns is secondary coil is higher than the number of turns in primary coil, and then the voltage in secondary is higher than the voltage in primary. However, current in secondary is lower than the current in primary. Okay, for the step down transformer, the voltage in secondary coil, okay, let's put the number first. The number of secondary coil is lower than the number in primary coil. The voltage in secondary coil is also lower than the voltage in primary coil. However, the current in the secondary coil is larger than the current in primary coil. Right? So basically how the transformer look like, we have two coils, One you call it as primary, another one you call it as secondary. So we supply the AC to the primary coil, and there's no direct contact between the primary and the secondary coil, but the EMF will be induced in the secondary coil. So EMF induced in the secondary coil, and therefore current will flow, and this current is called as induced current will flow in the secondary coil. So in primary coil here is I primary, in secondary coil where the current induced is called as I secondary, and the EMF induced here we call it as V secondary, and the voltage in the primary of course is V primary, right? So since we're applying the AC voltage to the primary, and therefore the magnetic flux, all right, exists in the coil. Okay, this coil is basically a solenoid. Magnetic field exists in the coil is also fluctuated in a sinusoidal waveform, and therefore since there is a change of magnetic flux, and EMF will be induced, all right, because magnetic flux or magnetic field is proportional to I, and the change, and when I is changed, B will be changed as well. So when there's a change of B, create the change of magnetic flux, therefore EMF will be induced in the secondary coil. Okay, this is actually the concept of transformer, right, from Faraday's law. So how can we get the I induced here? So I induced here is basically, you can apply it from Ohm's law. So Ohm's law is that E induced is equal to I induced multiplied with R. So from here, you're able to find out what is the I induced, right, in the coil, if you know what is the E induced from Faraday's law. Okay, so let's look at a very special case that is inductor. Okay, inductor. So inductor is basically a coil, single coil. Okay, for example, I have an inductor, and this is the inductor. And when you supply the AC current to the inductor, where the current is fluctuating, so the magnetic field exists in the inductor will be fluctuating as well, and the E will be also induced, right? E will be induced in the coil. So this E induced is called as back EMF, because according to Lenz's law, it's always opposed to change, and it can be proved that the back EMF induced in the single coil of the inductor is negative N delta flux over delta T. So where N is the number of turns of this of the inductor of the coil, and delta flux over delta T will be the rate of change of flux. So it can be proven out where this is from Faraday's law actually. So where is also equal to negative, this EMF induced is also equal to negative L delta I over delta T, right? So therefore L is equal to N flux divided by I, right? This L is called as inductance. That's how we get the definition of inductance. Okay, this is inductor. And do we have the relation to get the mutual inductance? Yes, if let's say we have, for example, a transformer consists of a mutual inductance, all right? So let's look at the mutual inductance now. So since the in a secondary coil, the E induced in the secondary coil is due to the change of flux in the first coil, right? Therefore, E induced in the secondary coil is also equal to negative, and flux, the rate of change of flux, is also equal to negative M delta I1 over delta T, right? So because it's a change of flux in the first coil, therefore the change of flux in first coil is due to the change of current in the first coil, right? In the primary coil. So this M here, we call it as mutual inductance. Mutual inductance. So it's also defined as mutual inductance. We use the symbol of M. It's also defined as the number, the flux linkage, which is the number of turns multiplied with the flux to get the flux linkage to the current. So basically, there are two mutual inductance in transformer. One we call it as mutual inductance on coil 2 due to coil 1. So due to coil 1 means due to the change of current in coil 1. So this flux will be in 2 and 1. Right? So there's another one we call it as mutual inductance in coil 1 due to the current in coil 2. Therefore, the definition will be mutual inductance of this is flux linkage. So this product we call it as flux linkage, right? And the mutual inductance in coil 1 due to the current in coil 2 will be N multiplied with flux in coil 1 to 2 due to current 2. So here will be I2.